Causality appears everywhere in physics. Every prediction assumes it. Every experiment depends on it. And yet physics has never defined what causality physically is. When a planet accelerates toward a star, we say gravity causes the motion. When tides rise and fall, we say the moon causes the change. When an orbit curves instead of continuing in a straight line, we say a force caused the deviation. Physics calculates these motions with extraordinary precision, but nowhere in its fundamental theories does it specify what physically makes one event produce another. It gives equations, it gives constraints, it gives evolution rules. It does not define causal substance. This investigation isolates that absence. Not whether gravity works, not whether predictions are correct, but whether physics contains anything that physically constitutes causation at all. In physics, causation is not a slogan. It is assumed operationally. When physics treats A as a cause of B, three things are implicitly in play. First, dependence. If A changes, B changes in a predictable way. Second, constraint. Not everything can follow from A. Only certain outcomes are allowed. Third, connection. There is some physical link by which B is produced from A, not merely correlated with it. Physics is extremely good at the first two. It encodes dependence in the way outcomes vary with initial conditions. It encodes constraint in the way laws limit what can happen next. But the third requirement, a defined physical mechanism of production, is where the question becomes sharp. If causation were defined inside the theories, we would expect to find it as something the theory can point to, a primitive, a mechanism, a named ingredient that does the causing. The question here is narrow. Where inside the formal structure of physics is that mechanism specified? Begin with the simplest case. A planet moves through empty space, far from any star. In classical mechanics, if no forces act on it, it travels in a straight line at constant speed. Its motion is described by two rules. First, its velocity remains constant. Second, its position updates according to that velocity. Nothing else is required. The equations predict a straight trajectory extending indefinitely. Now introduce a star. At some distance, the planet begins to deviate from its straight-line path. Its trajectory curves inward. Its speed changes. Over time, the motion closes into an orbit. The theory explains this by adding one element: gravitational acceleration. The planet's acceleration at each instant is proportional to the star's mass and inversely proportional to the square of their separation. With that addition, the straight line becomes a curve. But examine what has actually changed in the formal structure. Before the star, the equation specified constant velocity. After the star, the equations specify that velocity must change according to a rule tied to distance. The motion is not described as being produced by a substance. It is constrained by an added term in an equation. At time t, the planet has position x and velocity y. The gravitational rule assigns an acceleration, a, based on the current distance to the star. That acceleration updates the velocity. The updated velocity updates the position. The entire orbit emerges from repeated application of this mapping. The theory does not describe a physical process that travels from star to planet at each moment to generate the acceleration. It specifies a relationship. Given this configuration, the acceleration must have this value. The planet's path is determined by continuous recalculation of state according to that relationship. If the star's mass doubles, the assigned acceleration doubles. If the distance increases, the assigned acceleration decreases. Dependency is encoded. But what physically makes the velocity change? The equation does not identify an entity whose role is to push the planet. It does not describe a medium that carries causation. It assigns acceleration numerically. Even when gravity is reformulated in general relativity, the structure shifts, but the pattern persists. Instead of force, we speak of curvature. Mass and energy determine the curvature of space-time. The planet follows the straightest possible path within that curved geometry. Again, the motion is determined by structure. Given this curvature, the path must be this geodesic. But curvature is a description of geometry. It is not introduced as a causal agent with defined physical substance. The theory provides a rule. In this geometry, motion unfolds this way. It does not provide a primitive called cause that performs the unfolding. From inertial straight line to curved orbit, the only change in the formalism is the introduction of a rule tying acceleration to configuration. The orbit is the cumulative result of lawful updating. The equations constrain each step. They do not specify what physically generates the transition from one step to the next. Gravity predicts the orbit. It does not define what causation physically is. Now consider a quantum case. Two particles are prepared together in a joint state with correlated spin. They separate and travel in opposite directions. Later, two detectors measure their spins along chosen axes. When one detector registers spin-up, the other registers a correlated result. The statistical correlations violate inequalities that any local hidden variable model would satisfy. Experiments confirm this repeatedly. The mathematics predicts joint probabilities with remarkable precision. But what does the formalism actually contain? It contains a state vector describing the joint system, a rule for how that state evolves, a probability rule assigning likelihoods to measurement outcomes. Notice what is missing from that list. There is no element in the formal structure that specifies a physical event traveling from one particle to the other at the moment of measurement. There is no defined carrier that departs from the left detector and arrives at the right. There is no mechanism described that transfers an influence across space at the instant a definite outcome appears. The dependence between outcomes is encoded in the shared state description, not in a defined exchange of causal substance. It does not contain a description of a physical signal traveling between particles at the moment of measurement. It does not identify a mechanism that produces one outcome from the other. Bell's theorem shows that no model based solely on local, pre-existing properties can explain the correlations. This blocks one simple interpretation, that each particle merely carries hidden instructions revealed upon measurement. If that were the case, the observed statistical pattern would obey certain bounds. Experiments show that it does not. Yet, the formalism does not replace locality with a defined causal mechanism. Instead, it encodes a global state. That global state is mathematically sufficient to generate the joint statistics. Given the preparation and the chosen measurement axes, the probabilities are fixed. The structure constrains what combinations of outcomes are allowed and how frequently they occur. When one measurement occurs, the formalism updates the state used to compute probabilities. This update is a rule inside the theory. It is not described as a physical process propagating through space. It is not introduced as a field disturbance traveling outward. It is not specified as a mechanism with spatial extent or temporal duration. It is a change in the state description used for calculation. The dependence between outcomes is real. The production mechanism is not specified. Quantum field theory adds interaction terms and exchange particles. But even there, the exchange particles appear inside a calculational framework. They function within amplitudes and perturbative expansions. The formalism tells us how to compute probabilities of scattering events with extraordinary accuracy. But the formalism still consists of operators, amplitudes, and symmetry constraints. Scattering amplitudes are computed, and experiments agree. Nowhere is there a primitive labeled cause. The theory guarantees correlation. It does not define causal substance. Across gravitational motion and quantum entanglement, the pattern is consistent. Physics provides state descriptions, equations of evolution, constraints on allowable interactions, probability rules. These components allow precise prediction. But physics does not provide a defined entity whose role is to produce events. It does not provide a primitive specifying what causation physically consists of. It does not provide a mechanism identified as the generator of transitions. Instead, it provides mappings. Given an initial state, the formalism yields a later state. The mapping is exact, but a mapping is not an ontology. If causality were formally defined, it would appear as part of the theory's inventory, alongside mass, charge, or curvature. Instead, causality appears as an interpretive assumption that lawful evolution corresponds to production. The equations constrain what must happen. They do not define what makes it happen. Causality is indispensable to physics. Without it, experiment loses coherence. Prediction loses meaning. Explanation loses direction. Yet when we examine the formal structure of gravitational theory and quantum mechanics, causality does not appear as a defined physical ingredient. It appears as lawful dependence, as structured evolution, as constrained correlation. Physics can calculate how events relate with extraordinary precision, but it cannot say what physically makes one event produce another. Causality remains assumed everywhere and defined nowhere.